Welcome back, ladies and gentlemen. This is the third lecture for this is the lecture for chapter 3 or lab 3 for analytics of business intelligence. And today what we want to do is we're going to discuss what we call exploratory data analysis. If you recall, the first thing we did, the first thing we did in class is basically I broke down data tables for you, right? Obviously how we store data, how do we manipulate it into R. And then from there, we talked about cleaning the data, which, even though we spent like one slide on it, in reality, it's a very, like we talked about last week, it's a large part of the data science world and a large part of what corporations do. Today, we want to talk about getting into the nitty gritty about exploring the data you have. Again, when you talk about job descriptions like data analyst, data engineer, even some data analytics, right? Analytics engineer, all this kind of stuff. This falls into basically analyzing the data, right? In some aspect or another. So we want to discuss today exploratory data analysis. This is the next step. This is the immediate next step right after you clean up the data, right? Now the term is actually attributed to a statistician named John Tukey in his book, Exploratory Data Analysis. Check out the book. I think you'll find some snippets of it online. And essentially, right, his meaning was that, look, you have to examine a data set to discover or understand the underlying characteristics of the data, right? And he emphasized visualization. So another term that goes hand in hand with exploratory data analysis is a term called visual analytics. And I believe we have a class in this as well in the AIM and MITA program. Great class, right? The whole class just focus on visual analytics. I believe they use R in that as well, right? And the point is that you want to analyze and determine what step you should do now. Now that you've cleaned the data, you have a data set that you can actually use to some degree. You want to now figure out, hey, do I need to gather more data, right? Or are there some hypotheses that are being implied from the data that I can start testing? And this obviously leads to our next chapter, right? Hypothesis testing. And more importantly, like what models should I develop on the data, right? So in this chapter, we will basically cover 4 topics related to exploratory data analysis. Understanding first of all, what exploratory data analysis is. Analyzing a single data variable. By a single data variable, we're talking about like analyzing a single column. That's what we're talking about. Analyzing 2 variables together. You guys pretty much know what I'm implying here at this point. And again, that's analyzing 2 columns. What relationship to 2 columns, right? And exploring multiple variables simultaneously. Exploring all the columns in a lot more of the columns in one go. For this particular video or this particular lab, we're going to be using Chapter 3 marketing data. Chapter 3 marketing data that's posted on Canvas in the modules. All right, so John Tukey, in one of his statements he made, he said, an approximate answer to the right question is worth a great deal more than a precise answer to the wrong question. Questions matter, right? Questions matter. Questions, like I said before, they really drive what data science is all about. They really drive what analysis in general is all about. Quantitative finance, quantitative investing, everything, right? Everything quantitative and analytics related. But how do you know what question to answer, right? We saw when doing basic summary analysis, something stood out, right? When we were doing this when cleaning our data. For example, with the weather, I don't know if you guys noticed, but the spring weather had much worse weather than our winter weather, right? Which didn't really make sense, right? So something odd like that from our previous lecture, that drives the question, like what's going on? Is this something to do with the location of where this data is generated? Is the data correct? But these are questions that are being generated, right? Natural questions on the data. This is what's important. And John Tukey pretty much points out that, look, when you're talking about analysis, if you have the right answers to the wrong questions, who cares? That's not doing anything for me, right? It's much more important for true analysis at any corporate level to get an approximate answer to the right question that needs to be asked. Now, a lot of you guys, again, you've interned and you're working, you will notice your firm generates a lot of reports, right? There was one study done that around like 70 to 80% of these reports are not, no one reads these reports, right? 70 to 80% of these reports are not being read, right? What's happening there? Why aren't they being read? First of all, why is people doing it? One, people do the reports for political purposes. It shows the more reports you do in corporate America, in a lot of these departments, the more quote unquote work you do, the more quote unquote importance you have, right? That's one sad fact. But another reason these reports aren't being used because these reports are answering questions, beautiful reports. They're answering questions that to answers that are not relevant to the business at hand, right? That are not relevant to the business at hand. So, I mean, look, in the corporate setting, you got to do what you got to do. The hustle is real, right? But in terms of pure data analysis, trying to get to the heart of some sort of analysis, right? We have to ask the right questions. Data analysis, especially this stage of the game, this particular stage of exploratory data analysis or even visual analytics, it's about what questions you can generate, right? It's all about, hey, what are the good questions you can generate? And when you go about answering those questions that are being generated, more questions come up, right? More questions come up. And it's leading you towards a path of pure analysis of the data and information at hand. So that's basically the gist, that's basically the philosophy of exploratory data analysis. All right, so first things first, let's load up the Chapter 3 marketing data. At this point, you guys are pros at this. And again, right, strings as factors. We talked about this last class about levels and strings as factors. I want to decide that, right? So I uncheck that, I import it, and we are good to go. It's loaded in, all right? So my data is already loaded in. I'm going to go ahead and create a new script file, or I know some of my students already talked about you guys use R Markdown or R Notebook. Again, whatever you're comfortable with. I teach you guys in the R script files because the pure code goes in the R script file once you're done prototyping and learning or whatever you're doing. But for learning purposes, by all means, please use what you'd like. Alrighty. I shall call this Lab 3. Alrighty. So I loaded up my data. Next thing I'm going to do is call in library data.table. Remember we talked about this, we had a Q&A session where we were talking about, how do you know which libraries your code needs? It's kind of an open-ended issue. Hopefully you have a somewhat competent analyst you're working with. Sometimes you don't. But remember, when you're typing in your script file, please make sure your libraries are always on the top, right? That's the proper way to do it. So I got my data table ready to go. And I'm going to create a new table, right? If you have the memory for it, I always like working with a second table, because in case I mess up the original table, I can always load it, call it back. All right, notice I'm using the copy command. Again, just as a reminder, in R, with using data tables, we have to use the copy command because data tables, sadly, are like pandas tables in the sense that because they're so hyper optimized for memory and speed and all this other stuff, when you do mark, if I just did mark equals chapter 3 marketing, then just like in pandas tables, mark and chapter 3 marketing are basically pointing to the same table. So if I change one, I'm changing the other. If I change the other, I'm changing the other one. It's not two tables, it's one table pointed at the same one. This is why in R we use the copy command, right? And in pandas, you have your own version of the copy command, all right? That's more of a method, if you will. Alrighty, so I'm using copy command. I mean, funny thing, by the way, I used the copy command already, right? But chapter 3 marketing is a normal data frame right now. It's not even a data table. So let me go ahead and convert my mark table into a data table. And we can confirm this just like in our slide, all right, by using the str command. I didn't, here in my slides I didn't do it, but you guys know from our previous slide, our previous class. What are we going to do? Let's view the table. Okay, it's a data table. I confirmed it. I have 1, 2, 3, 4, 5, 6, 7 columns. Fantastic. I have Google AdWords, Facebook, Twitter, marketing total, and revenues. These are all numbers with decimal places. The numbers actually look like numbers, they're not quotes, so we're good there. I have another column called employees. That's an integer. All right, cool. And I have one column called population underscore density. That is a string, high, medium, high, medium, high, medium, right? Let me find out how many individual values there are, right? Remember our Miller's law? Guys, remember Miller's law? So I'm going to run the unique command on the mark table, the density. Oh, fantastic. High, medium, low. So there's a column called looks like it's population density. That is implying high, medium, and low. All right, fantastic. All right, so what's the first thing we have to do, guys? We have to address the fact that our character column should not be a character column, but that it should be a categorical column. Now, my first question to you guys, is that a ordinal categorical column or is it a nominal categorical column? Right? Remember, is it a nominal or is it an ordinal? Well, the question is, does this categorical data, does it have some order of magnitude? The answer is, it does. High, medium, low. Medium is greater than low. High is greater than medium. This is a ordinal categorical column. So therefore, I'm going to go ahead and I'm going to convert the pop density column into a factor or a categorical column of ordinality, right? So here, I'm going to do mark all the rows. The name of the column is pop underscore density. That pops up for me. Colon equals, and now I'm going to call the factor function. Boom. All right. The first parameter, again, is the column that I'm going to convert into a categorical column. All right. My next one is basically what are my levels? Okay, what are the levels? What are the values that should be or are in that column, right? In this case, I'm going to state them as low, medium, high. Now, why am I going to state them as low, medium, high? All right, because I know this is going to be ordinal and I want to preserve the order in order of magnitude. Remember, every time you're putting the order of magnitude, go from the lowest to the highest, right? Or the smallest to the largest. Okay, so in this case, I have to use the C function. And remember here, some of you will make an error here. What's the error people are going to make? You're going to mess up the uppercase or lowercase. That matters, all right? That matters. So because the values are all uppercase, I have to use uppercase. If I use lowercase, what's going to end up happening is when you run this line and you look at that column, it's all going to be null. Why is it going to be null? Because you define that column to be a categorical column, ordinal categorical column, to only allow the values low, medium, high in lowercase letters. And when it looks through the column, it's not gonna see any of those words in lowercase. So any of the uppercase words, it's gonna simply null them out and say, hey, you guys don't belong here. The only values that belong in this column are low, medium, high in lowercase. So please, when you're dealing with alphanumerics like this, because before in lecture 2 we dealt with numerics, right, as categorical columns. Here we're actually dealing with actual words as categorical columns. So be cognizant of this, right? And also, when it's ordinal and you do have alphanumerics, then you must put in levels, right? Because how the heck does R know, right, which one is the lowest or the smallest and which one is the greatest, right? How does it know the order of magnitude? You have to explicitly state it. So that's why I have to put low first then I have to put medium, and then I have to put high. All right, and then finally, I have my last parameter. And if this was a nominal, if this was a nominal, if this was a nominal, nominal categorical column, we would be done at this point. But because of the fact that this is an ordinal one, I have to literally use this last piece of parameter called ordered, and say, hey, ordered equals true. And now I can run this. And now if I run str again, guys, you see, let me zoom in a little bit more. I think that's good. And now you can see, right, again, everything's the same, but now look, population underscore density is now says literally ordinal.factor with 3 levels, low, medium, and the other one gets cut off, but you can see that it does have the right order. It does have the right order. All right? So now it looks like we're pretty much good to go. Now, oh, sorry, there's one thing we didn't do. What did we forget to do, guys? That's right, random person watching the video. We didn't check for nulls. So let us check for nulls. How can we check for nulls? Well, I showed you guys before, just use the grep command. Grep, call the table, the value I'm looking for is NA, and I can call the grep function. I'm sorry, I don't think I showed you guys. Did I show you guys this? Well, I'll show you guys now in this video. You can call the grep function, right, on the whole table. So if I do this, right, notice I got integer 0 back, right? What does that mean? That basically means, hey, there is no columns out there. There's no NAs and no columns. There's no NAs out there. We're done. You're done, right? So at this point, I have no NAs. I have no values out there. And now I'm good to go. And just to remind you how grep works, guys, right? Grep, I mean, we were using grep to look for certain patterns in words, but even for nulls, you can use grep. If I were to quickly create a sample table, let's do 1, 2, NA, B equals 3, NA, 4, right? And now and then I'll create another DD table. I'll call this DD for short. A comma B. And now I'll do grep NA on DD, right? Look what you see down here. You see how you get a 1 and a 2? What is that 1 and 2 basically saying? What is that 1 and 2 basically saying? It's basically saying, hey, in your first and second column, you got NAs, right? In your first and second columns, you got NAs. So for example, if I had a second, let's do, let me rewrite this. Let me steal this, put this in the D column, and for B, we'll just do a normal 1 to 3, right? Now we'll call this ABD. All right, so now at this point, guys, just so you can see what DD is going on right here, down here. So now I have 3 columns. The first column has an NA, the third one does, but the second one doesn't. So if I run this now, right, you see that it gives you back the values 1 and 3, the grep command. Again, very powerful grep. I'm not even using it within the data table with the way you used it before with finding patterns. I'm just using it on the whole table. And so literally it's giving you the values 1 and 3, telling you that, hey, the first column has an NA, the third column has an NA. Oh, and by the way, we're just searching for NAs, for nulls, right? You can use this trick if you're searching for any kind of pattern throughout a table. Think how powerful that is, right? If you're looking for certain values across a massive amount of table, across all the rows, right? And you're trying to hone in which columns have those values, boom, just like that, right? Again, great tool, grep. So that's just a little refresher for you guys. If I go back to number 9, here, I'm going to highlight this. I think if If I do, boom. Some of you guys are wondering, by the way, how did I just do that? How did I just highlight multiple lines together? If you are in Apple, highlight the lines, then press Shift Command C. That will comment it. And of course, Shift Command C will uncomment it, right? Same thing. For my PCs, you're going to use Control Shift C and to comment it, and again, Control Shift C to not comment it. So that's a little trick in R, guys. I just wanted to show you that. All right. So like I was saying, okay, good. We have no nulls. I'm good to go. Now let's move on to analyzing. I mean, we pretty much did the analyzing and adjusting the data, right? As we're looking through the data, we see that, look, we have expenditure costs for Google AdWords advertising, hypothetically in this data set, expenditure costs for Facebook advertising, expenditure for Twitter advertising, right? And then there's a total marketing, and there's a total marketing budget. There's a total marketing budget over here, right? So again, if I want to confirm some things about the table, right, I have my mark, click that. I have my mark table right here. Let me close my chapter 3 one. Right, we can see that, you know what, Google AdWords, Facebook, and Twitter, if we wanted to add this up again, we could see that, hey, you know what, it equals to marketing total. So marketing total is basically the summation of Google AdWords, Facebook, and Twitter. If we wanted to, we could add it up row by row. You guys know how to do that. Or I'll show you guys how to do that a little bit later. Actually, no, you guys know how to do that with column mathematics. Column mathematics. All right. So, and we have something else called revenues. Right. Interesting fact. Right off the bat, you guys notice something about these numbers as I look at them? Why is it that the revenues are less than marketing total? That doesn't really make sense. Shouldn't revenues be greater than marketing total? So look, the reality is probably these numbers are probably in a different format than these numbers. Meaning, these could be like, I don't know, 100, like a thousands or in thousands, and this could be like in 100,000s or something along those lines, right? So right off the bat, probably this could be a mistake, or this could be horrible companies, or the scales are off, right? But that's what I'm saying, right? Right off the bat, that's what I'm saying. We know that these three summate to this marketing total, and we can confirm that if you do some math. When right off the bat, we're saying, hey, why is this greater than this? Shouldn't revenues be greater than marketing total, unless this revenues means something totally different, or maybe it's a different scale. But nevertheless, we just created questions. We just created questions. This is how analysis goes. Before you even get to the core of your analysis, you have to ask questions about the data itself, which will open itself up to asking questions about the analysis on it, right? Or the different analytics around it, the descriptive analytics. What is the data implying? What happened with the data? Your diagnostic analytics. Why did this happen according to the data? And then so on and so forth. All right, so we also have number of employees for each company. So it looks like what each company spent on different advertising, what their marketing total was, what the revenue was, how many employees it has, and then of course population density probably now implies, hey, where that company is operating, right? In the city, what's the population density of that city, per se. All right, now the first thing you want to do is, if we take any particular column, you notice we have a lot of numeric columns over here, right? If I run the str command again. All right, we have a couple, most of them, -1 is, numeric columns. So what do we do with numeric columns, guys? If you guys remember, take a summary of the bad boy, right? Summary statistics. You guys remember this from stats? What is your summary statistics? Well, we usually call them we usually call the 5-number summary, right? But we have the 5-number summary. We also have something with those 5-number summaries and the mean. But again, my original question: what's our summary statistics, guys, on numbers? Min, max, first quartile, third quartile, and median. You guys remember that? Min, max, first quartile, third quartile, and median. This gives you a summary of all the values in that column, right? A breakdown of the summary of all the values in that column. This is back in your world of stats, right? So how do I do it? Easy. Let's take a particular column. Let's take Google AdWords. Mark, Google AdWords, done. And down here, it gives you your summary statistics. But notice something else it gives you guys. It gives you the mean. The summary function, right, gives you their 5-number summary along with the mean, right, along with the mean. Now, who remembers why do we like to compare median and mean? All right, it's from stats. Well, firstly, which statistic, if you will, gives you is more affected by outliers, meaning larger or smaller numbers, right? The median or the mean? That's correct. It's the mean. The mean is extremely more sensitive. It's affected by outliers of the numbers, right? So in a situation where your median and mean are similar or even the same, that implies that the data has not necessarily any outliers, and it also can be normally distributed. Because if you guys remember the normal distribution, in a normal distribution, the median and the mean are exactly the same. So if they're similar, there can be an argument here that hey, maybe this data is normally distributed in this particular column. All right, so that's how we do the summary. And of course, another way to do it, right, I could call it on the column like that, or I could use it within my data table as well. So on all the rows, I can call the summary function on Google AdWords. Right, same way. So lines 16 and 18 are give you the exact same thing because we're doing the same thing. In line 16 and 18, we're just calling the summary function 2 different ways. We're calling the summary function on the Google AdWords column 2 different ways. All right. The 5-number summary in general, as a reminder, it actually provides information on central tendency, right? That's why we have the median, the quartiles, right? The quartiles. If you were to split the data according to the median, right? The quartiles are basically the medians of those 2 sets of data. So that the spread is basically the quartiles within the 50% range. And then the range itself. And range is always minimum and maximum, right? The spread, this is like stats buzzwords here. The spread is always the numbers between the quartiles. The range is always the numbers between min and max. All right. So we can also use the summary function to take a summary of the categorical data, right? Recall again the categorical data. We have here is pop density, right? These values right here, high, medium, low. So we can call summary on this as well. And in this case, what happens here, what it's basically doing is counting all the unique values. So in this situation, we have 68 iterations of low, 52 iterations of the medium, and 52 iterations of the high. All right? So that's what the summary does on categorical data. So that also gives us some sort of summary about the information. Now, we talked about visual analytics, right? So visualizing data, visualizing these numbers. Look, we showed these numbers here, and they're fantastic, right? Fantastic, great numbers, the greatest numbers ever, right? But numbers are just numbers, right? Even when we were talking about Miller's laws, numbers are just numbers. To understand magnitude, we are visual creatures. It is so much easier and effective to do analysis or to see differences or nuances visually versus just looking at the numbers, right? I always make this joke about how, as human beings, ladies, the first time you see a man, the first thing you notice is their physical appearance, and then you get to know the individual, the individual personality of the individual, right? Fellas, same thing, right? And it just stops there, right? There's no depth or personality from there. For guys, purely very shallow, right? So this is a joke I usually make, but the point I'm trying to hammer home is that we always notice things, people, situations visually first. Right or wrong, it's always visual first, and then slowly we understand the situation from an intellectual point of view, right? Data, no difference, no difference in data. It's an incredibly powerful tool, incredibly powerful way to analyze information, and this is why visual analytics. This is why we have a separate visual analytics class. That's number one. But this is why visual analytics is so hot and so integral and critical to the exploratory analysis part of analytics, right? So we're talking about graphing here essentially. Now, R has natively built-in functions that you guys probably use in other classes or at other jobs, internships, what have you. The plot functions, they're fine, they're fantastic, people use them, right? I don't knock them. But data analysts tend to use a package called ggplot in R. And the reason why they use this separate, and it's kind of weird using ggplot versus the plot functions, but there's a method to the madness, right? And the reason why they like using ggplot is because ggplot is incredibly powerful from the point of view of doing visual analytics or exploratory analysis as a whole. Because the way the language is structured, the way the commands are given, they're given from a point of view that align with the thinking or the let's put this the framework that one would use in doing visual analytics, right? So the program, the language itself, the syntax of ggplot aligns with the framework of how visual analytics should go. And this is why ggplot is used by data scientists, data analysts, visual analytics. Is the reason behind it. I've once had a student that was an internship, and he was in ggplot, and he was being criticized by his superiors, right? His analytical superiors are like, "Why are you using ggplot? It's so much more work. You could just use plot, right?" And he told me about it, and I asked him, well, what is it? What you guys were doing? He's like, "We were just basically making reports." I'm like, "Yeah, that's why." All right. I mean, if you're making reports, you're making reports. That's fine. ggplot is for, again, exploratory analysis is to be a detective of the data, right? You're being essentially a detective of the data. So when you're analyzing something, that's when ggplot, right? That's why you would take on the headache of ggplot versus just using plot. But for me personally, I feel ggplot's a lot easier for me than plot functions, just because the structure of it, I feel, do I have a lot more flexibility and control. But I mean, to each their own. To each their own. Right now, again, ggplot is a third-party package. So I'm going to, and by now I think you guys are experts on this, I'm going to go here and install ggplot. So for most of you, you have to install ggplot for the first time. I'll do it for you guys right here. Type in ggplot right here. Remember, go to lower right window, go to the middle tab that's packages, click on install. Type in the package you want. And by the way, when you're typing in these packages, look how many packages there are over there. So by the way, I want ggplot2, not ggplot2 movies. For the movie producers and directors in here, you can explore the ggplot2 movies on your own, and I will install it. Oh, so I already have this. So it's asking me, do I want to restart R? I'm going to say no, but you guys go ahead and restart it for your sake. Now look, from here, again, it's asking me the question, do I want to install source packages which need compilation? No, I don't want to install anything that needs compilation. Just say no and let it do a soft upload. You don't need all that compilation nonsense. And as you can see, it's unpacking a lot of stuff. All right, and you should be good to go right there as you guys are downloading ggplot. So I have ggplot now. Hopefully you guys will too after this. I'm going to save this. And now we are ready to use it. Now, building a ggplot, right? Building a plot in ggplot. And we always like to use the term build a plot in ggplot because ggplot is basically layers on top of each other. That's the whole concept behind ggplot, right? You have a standard graph, and then you keep adding levels to that graph for analysis purposes. Now, the data you're visualizing in a ggplot, it must be a table. So you always have to put your table in a data table. You always have to put your table in a data table, right? And the variables or columns, we map them to different aesthetic attributes, what we call aesthetic attributes, right? And by aesthetic attributes, I mean, we can think of things like, think of it in a simpler way to think about it. Think about like the rows and columns, or the x-axis and the y-axis. That you can consider that like an example of an aesthetic attribute, right? So we want to map that. We also want to define our geometric objects, right? What do we mean by geometric objects? So geometric objects are basically, how do you want to visualize your graph? Do you want a bar graph? Do you want a line graph? Do you want a scatter plot, right? Also in ggplot, you can do statistical transformations in the graph itself, in the command itself. We'll save that for linear regression, right? I'll show you guys how to use the statistical. There's a whole statistical package that comes with ggplot. You can also scale different values in the aesthetic space. We can do faceting, right, which is basically showing subsets of data within the data set, right? I'll talk about that as well. And in the Titanic data part, I'll talk about that. And you can coordinate the different, the plane of the graphic with different systems, add a couple other things, et cetera, et cetera. So, I mean, we do all these things, right? This really won't make sense to you unless you do it. So, I mean, here's a basic breakdown of a ggplot, right? There's a ggplot function, and then you can put your data set in there, and then you can define, hey, how you want the data set to be visualized, and within that visualization function, you could put your aesthetics command, where one thing goes versus the other, et cetera, et cetera. This is quite flexible. I put my aesthetics command always in the main ggplot function, but you could have them in the individual geometric objects as well. And time to time, we tend to do that. From time to time, we tend to do that. So you'll notice a plus over here, right? There's no math going on. What happens is that plus is basically used to layer commands on top, one on top of another, one on top of another, right? So again, I like to bring up that point of layering. So I mean, look, we could talk about it, or we could do it. So let's just do it and jump into it, all right, guys? So let's do a bar graph. Let's start off with a bar graph. So we're going to make a bar graph for the population density column. Now, why are we going to use a bar graph on the population density column? It is because bar graphs are used to visualize categorical data. Bar graphs are used to visualize categorical data. That is why. All right, so our categorical column is, we have just one column in our table, pop underscore density. All right, so how am I going to graph this? Well, firstly, I need to call ggplot. All right, notice it ran, and I'm good to go. All right, now notice that I'm good to go. Now, we start off with the ggplot function. Oh, looks like I had some sort of error. Hold on a second, let me pause this and make sure everything's okay on my end. I mean, it looks like everything is okay. I think the problem is after I downloaded ggplot, they wanted me to reset my RStudio. I haven't done it. I'll worry about that after I finish the video. But for you guys, let me do the graph. You guys obviously reset your video when you're doing it. So let's try this. Let's see if ggplot works. All right. So the first things I use is the ggplot function. That's number one. That's always going to be there. The first thing to do is I place my data table there. And then from there, I'm going to call the aesthetics function. Oh, looks like I got it again. Okay, let me just restart my machine because it's causing problems. Just hold on a second. It won't make a difference to you guys because you're on video anyway. So I restarted my RStudio, and some of you guys might see this error, so I wanted to show you guys this error in the video. So when I call library R, right? It gave me this warning message about rlang must be at least version 0.0.80. This could be a factor because I didn't update my R. Shame on me. Um, but it's asking me to update dplyr and then install with install packages. Again, when it's asking you to update a certain package and then restart R, you're just going to go here to your install again and literally just click install right here. Type in the package it wants you to do. It's occasionally, it should really, our studio does a great job in taking care of this automatically. But I mean, occasionally you'll have these situations where they say, hey, look, update this package. So I'll go ahead and install this one. And I'll say, yes, do you want to click installing it? Yes, let's install it. And again, it's going to ask me, hey, do you want to do from compilation? No, not from compilation. All right. All right, and again, it wants me to reset it, so I'll just reset this one more time. Okay, so now it's the second time I'm resetting it after I install that other package they asked me to install. And so firstly, what I'm going to do is I'm going to run my library data table, make sure I have that. Then I'm going to run ggplot. Now there's no warning, so now it's finally happy. And I just want to confirm that I still have my mark table. My mark table is still there, still a data table, so I'm good to go. If you don't have it, just run the other lines of code just so you're up to this point at this point. All right, so now I can do line 22. Now remember the first line again, the first parameter is the table for ggplot. That is the most important thing. After that, you have the option to put the aesthetics in the main ggplot function or the other graphing functions. That's fine, it's up to you. Me personally, I just like putting it in the main function, but that's me. But you guys can do anything you want, the way you want it. So here, like I said before, what we want to do, we want to graph the population density in a bar graph. In a bar graph, there's only one aesthetics, and again, aesthetics, think of aesthetics like the axes, the x-axis and the y-axis. In a bar graph, the only thing we define is the x-axis. We basically are saying, hey, which column are we putting on the x-axis, right? That's how a bar graph works. Then the y-axis is automatically computed by counting the individual items in the column, in this categorical column. So I want to put in pop density, right? And that's it. And then from here, all right, so here you have your function. I'm going to do plus because this defines my table, and this defines, because I'm using the AES function within the ggplot function, it also defines which columns I'm putting where. In this case, I'm just I'm using just the population density column, and I'm placing it on the x-axis. Then I do plus. Plus is another layer of command that goes on the initial ggplot command. And this additional layer of command I do is now the graph itself. Now, all the bar graphs, all the graphs in ggplot, they start with the term GEOM for geometry, if you will. When I type those letters in, you will see all these graphs at your fingertips available for you in ggplot, right? It's virtually endless. Okay? So for me, from here, what I'm going to do, I'm just going to choose underscore BAR for bar graph. That's it. I'm not going to put anything in it. Now again, you had the option to put this part of the line in here, right? So it can go either or. Again, I leave it up to you. I run the line, and in my window here to the bottom right, you'll see the plots pop up in RStudio. I'll click on the zoom button right here, and you'll see the bar graph in all its glory. You see that? All right. I can minimize this a little bit. And there you go, the bar graph. It has the count on the y-axis, the x-axis has the column, and now you guys can clearly see, oh look, I have my I have 3 unique values, low, medium, high. Low is about 60 something, population density is about 50 something, right? This is 50 right here. So here we have a breakdown of the values. We have a rough breakdown of the values, and we can visually see these two are alike, this is slightly more. Okay? Visual analytics in play. right? Of course, you can also expand this out and just see it here if you wanted to, right? Might be kind of easy. All right, from here, let me show you a nifty trick. Within the function of the bar graph, of the graphing function, there's a keyword called fill. And this basically fills in the color of the bar graph. So if I do fill equals blue, the bar graph becomes blue. There is another parameter for aesthetics purposes called color. And what color does, that controls the outer border of these objects. So where fill fills in the solid aspect of the graph, color does the outer perimeter, strictly the outer perimeter. So if I do red here, bam, I get that graph right there. You see that? So in the slides, I just showed you how to do fill. Later on, I'll introduce color in the slides, but just so you guys understand the difference, the fill is the actual colors inside. Color is the outer color. All right. Same thing with points. Points. You don't use fill, you use color. All right, so that's your basic bar graph. And again, you do bar graphs and categorical data. Now, what about numerical data? How do we graph numerical data? Well, the two most popular ways to graph numerical data, guys, are obviously box plots and histograms. Box plots and histograms. All right. So here, let's do a box plot first on Google AdWords. Mark table, aesthetics, x equals. Now on the x side, I'm just going to place my whatever it is that I'm graphing at this point, which is Google AdWords, right? But there is a time where we can put in more values in the and we can put in more values in the box plot, and I'll show you guys that in a moment. But first, for now, let us just do Google AdWords, all right? And I'm going to do box plot. And you get a very nice, simple box plot. Now notice my box plot is, I can show you right here. Notice something about my box plot, right, versus my graph over here. Why is it that my box plot here in Google AdWords, right, was this way versus this way? Because I did x-axis, put it on the x-axis. If I put it on the y-axis, and again, this is, you can place your, you can do your box plot horizontally or vertically. It's totally up to you. Right now, it looks like my slide here. Now it looks like my slide here. So I can put it on my x-axis with the box. When you're dealing with one column, you can put it on the y-axis and the x-axis, right? So I just wanted to show you that. Now again, here, right, when we're looking at Google AdWords, on the y, if I do this with my y equals Google AdWords, my values are going along the y-axis. They're going on the y-axis, right? My median is here, this solid line. My first quartile, my second quartile, my first quartile and my third quartile, these are what these lines are. This point right here is ideally, I'm going to say ideally, not all the time, but ideally it's the max, and this point right here is ideally the min. Box plots, when they graph it, they tend to, sometimes you have situations where the most bottom point isn't the min and the most top point isn't the max, because the box plots will graph outliers, as it defines it, outside of the box plot, as dots. And you'll see this. I'll show you guys this in a few moments. All right, so here's the box plot. And just like before, I can add a little color to it. Do a little fill equals blue. I think in my slide I do blue. And there you are, right? Make this like this, right? Like that, whatever, what have you. All right, so that's our box plot. And here, basically, the box plot is basically the visual representation of your 5-number summary, right? Again, min, max, median, first quartile, third quartile. It's all right here for you. It's all right here for you. Because we have no outliers, we know this is the min and that's the max. All right? I'll show you an example where we do have outliers. Now, this you guys should know from statistics, but as a reminder, what is defined as an outlier when you're doing a box plot? Well, an outlier is basically what happens here is the interquartile distance. So basically the point from this line to this line, right? Anything that is 1.5 times greater than this distance. So this line will go all the way up to 1.5 times this length. And this line right here will go all the way down 1.5 times whatever this length is, right? So if your min and max fall within those, like ours do, in this situation for Google AdWords, we have no outliers. But if we have min and maxes or any numbers that are going to be greater than 1.5 times this length going up, or less than 1.5 times this length going down, then you're going to see dots beyond these, what we call whiskers, the whiskers, and those are defined as statistical outliers. Now look, in terms of the data you're working with, they may not be an outlier, right? But nevertheless, it's all about visual representation for you to make that judgment call. When you see those dots, you're like, all right, why are these things 1.5 times the interquartile distance? Is that right? Is that wrong? What does that mean? Does it mean anything? Right? So that's for you to analyze. Nevertheless, boxplot does that for you, right? That's the whole point of boxplot and those outliers, which you don't see here. So we know right off the bat that, hey, our min and max is less than 1.5 times the interquartile distance. But you might see it in other situations, right? You might see other situations. Now, why did they choose 1.5 times interquartile distance here? Because of what I said before, right? The 5-number summary, right, can also categorize a normal distribution, right? So again, this is basically implying that, hey, there's an argument to be made that this data is normally distributed. That's where they pretty much got the 1.5 times interquartile distance, right? Goes back to the normal distribution. Everything goes back to the normal distribution. All right, so that's a box plot. All right, now what's another way to analyze a numerical data set? The histogram, the accursed histogram. Now, a lot of people don't like dealing with histograms because there's a misunderstanding about histograms, right? Because of the bar widths. The bar width could be anything you want. Case in point, right? Let's make a geohistogram right now. So again, I'm going to do Google AdWords. Right? And now I'm going to do GOM_histogram. All right? And that's all I'm going to do for now. That's all I'm going to do. Oh, sorry, I got an error. Hold on. I have to give some more information. With the histogram, I have to give, obviously, I have to fill in my x equals, it shouldn't be y, it should be x. All right, excellent. This is what I wanted to show you. I wanted it to be in the y-axis. So we get something like this, a monster like this. And you'll notice a little warning, or not necessarily a warning, but a statement comes up when you run that. Stat_bin, using bins equals 30, pick better value with bin width. What is that saying? Well, what's saying is R pretty much, we didn't tell R how many bins to have. If you remember, the whole deal with histograms is that we define, remember, histograms are used on numerical data. Bar graphs are used on categorical data. With histograms, we have to define the buckets or the groups, category or groups that the numbers will fall into. That's what we mean by width. Again, this should all be a review for you guys, right? That's what we mean by width. What the width should be. Either you can define the width of the bars, right? Or you can define how many bars you want. So here, what happens is, by default, because I didn't specify anything, bins was 30. So give me 30 bars. Now look, that's hard to see. So let's use some different colors. So in this case, let's do, in my slide I did yellow. I'll do pink here, right? And I think I did black. I'm going to do white. All right. And there, now we can clearly see this graph a little bit better. Okay, now we can see this graph a little better. There are 30 bars here, right? That's the default, 30 bars. And what happens is it makes those 30, it's going to make essentially 30 groups, and it's going to divide the numbers. It's going to make 30 equal size groups, and it's going to divide the numbers into each groups, so you can see how many numbers there are in a particular range, or in a particular range. Now let's say, okay, that was all right. That gave me 30 bins, but let's say I define the width myself, right? And again, I can firstly, I can easily change the bins. Let's go here and say, hey, you know what? I don't want 30 bins. I want 10 bins. So if you just type in 10 bins right here, you'll see right here. Okay, let me zoom it in for you guys. You'll see now I have 10 bars. Right? I have 10 bars now because I defined it as 10 bars. Alrighty? Okay, so I defined it as 10 bars. And here, instead of bins, I can use bin width. Bin width is the other side, where instead of saying I want 10 bins and you figure out what the group should be, I'm explicitly stating, hey, I want a bin width of size, in this case, 50. And that basically means put 50 numbers in each group. All right, put 50 numbers in each group. Then what happens is, if I do it like that, then the bars are decided by how many numbers there are, right? Either way, ggplot is doing some sort of mathematics. All right, so put 50 in each bin. So now what ends up happening here is, what does this mean here, right? What does this mean here? So we have this bar here. You notice the 0 over here? Okay, you notice the 0 over here? What does that basically mean? This means that this is going from 0 to 50, right? 50 to 100, 100 to 150, and this is why the number here is 0. This bar over here would be 50 if there was one. This one is 100 because it goes from, again, 0 to 50, 50 to 100, 100 to 150, 150 to 200, 200 to 250, 250 to 300, 300 to 350. All right? Did I mess up I think I messed up my counting. 0 to 50, 0 to 50, 50 to 100, and 100 to 150. All right? Now, with that being said, you notice that on the borders, I said these numbers twice. If I did have a value that was, so these are the actual values down here, the counts for the y's. Let me ask you guys this. If I had a value that was actually 50, hypothetically, right? So this bar is supposed to represent the values from 0 to 50, and this bar represents values from 50 to 100. If I had a value 50, where would it go? In this bar or this bar? Again, this should be a review for you guys. This is I think you guys also graphs in pre-algebra or something, or I don't know, something along those lines. So we're in a histogram. How does it do it? That is correct, right? You are correct. 50 falls into this bar right here, the second bar, not the first. Why? Because when we say 0 to 50, that second value is exclusive. The large side is always exclusive. Or let's put it this way, the right side of the bar graph is always exclusive. The left side is inclusive, right? So this bar right here, second bar has 50 to 100. So the value 50 goes in the second bar. The third bar is from 100 to 150. So the value 100 goes in this bar. And that's why you see the 100 lined up here instead of here, right? That's why you see the 200 over here, because the 200 here, this value, is going to be inclusive here, but for the fourth bar, it'll be exclusive. So any 200 value will fall into this bar, any 100 value will fall here, any 250 value will fall in here, any 300 value will fall in there. That's basically how histograms work. Now, it's not terribly apparent because of the way the bar graph, it slides, in the x-axis, it has the numbers. So you can shift these numbers and you could put your own scales in. And a little later on in our lectures, not this lecture, I believe it's I believe when we get to the into our clustering, I show you guys how to some other options within histograms to make these graphs more intuitive, to make these graphs a little more intuitive, and to change up the scales and all that stuff to make it work for you, to make it work for you. All right. So from here, I created my histogram. All right, excellent. Bin width 50. Excellent. I have this same graph, and let's go about analyzing real quick. All right, fantastic. 0 to 50, not that many values. I have a ton of values from 50 to 100, 100 to 150, 2 to 250. So the bulk of them are around there, right? So it looks like there's very few Google AdWords that were less than 50 pretty much, right? A bulk of them were between 50 to, I mean, it looks pretty evenly spaced out, right? It looks pretty evenly spaced out, at least in the way that graph is showing it, all right? So at this point, we're seeing the distribution. That's the beauty of the histogram. The histogram is giving me a nice little distribution of the numbers, how it works out. And obviously, the more detail you give it, meaning the smaller the width you make the bar graphs, like we did in the beginning, the more pictures you can get of the distribution of the numbers. All right, so that's basically how you analyze two numerical columns. I mean, there's two different graphs for numerical columns. Now, let's say, oh, again here, I show you guys how to. So in this particular slide, I pretty much showed you guys how to do the different bins and bin width and all that stuff already. All right, different colors, all that stuff. All right, now, let's run this back now for Twitter. Let's run this back now for Twitter, all right? Let's do a ggplot, let's do a box plot for Twitter, and let's do the histogram for the Twitter data. All right, and now, this is what I wanted to show you guys. All right, this is what I want to show you guys pretty much. You notice now this length right here, it gets maxed out, right? Because this length right here is 1.5 times whatever this length is here. Not the case here. So right off the bat, we know that, hey, look, our min value for Twitter fell within 1.5 times of our interquartile length. Our max length, or actually our max value and another value, they didn't. This is what these two dots are right here. This is what these two dots are right here. And this automatically shows you that, hey, you know what? The data is skewing to the high side. Is skewing, if you guys remember that terminology, it's skewing to the high side, to the higher price. All right, let us also knock out. So that's, we have two values that are defined as outliers from a statistical point of view. Our max value and another value, meaning they're 1.5 times greater. They're greater than 1.5 times our interquartile length. All right, let's go ahead and do the histograms now. And I think I do a 10 bin histogram for the Twitter data. All right, let me just make it a little bit wider so you guys can see the whole code. Just change this from Google AdWords to Twitter. And I run this. Let's zoom in over here. Oh, so I already have that window open. So here now, guys, we can clearly see, ladies and gentlemen, we can clearly see that, you know what? We do have a skewness on the data. Now, we didn't see this with Google AdWords. Google AdWords are pretty flat, right? Relatively pretty flat. But here, we have a skewed data towards the high side, right? We saw that in the box plot as well. And what we also see is a little bit of an outlier right here, right? We see a little bit of an outlier right here because we saw an outlier in our box plot. We saw an outlier in our box plot. And here we can see the numbers a little bit clearer. This could be much more clear with the baskets. And again, in lecture 5, I show you more advanced commands to make this clearer, so you have a more clearer picture of the breakdown of your groups. All right. Now, all right, so that's basic some questions we have. Hey, we didn't have any outlier data with the Google AdWords. We did have some outlier data with the Twitter data, right? Again, these generate questions. Maybe this is not a problem. Maybe this is the way the prices were given away. But there's definitely more of a condensation of numbers around these values, and then slowly they taper off, and there's some sort of outlier. Unlike Google AdWords, which was pretty much flat according to across the different price ranges. All right, so from here, right, so this is basically analyzing one column at a time. Can do it mathematically, we can do it by numbers, we can do it visually. But of course, it always comes down to comparisons, doesn't it? Right? So and we can also analyze, and we should analyze, right? This is obviously leading up towards regression or some sort of relationship or defining some sort of relationships between variables. Analyzing two variables together, right? And you sometimes want to test these relationships between data if it exists, if it's there, right? So there's 4 questions that serve as a guide, essentially. What does the data look like? All right? Is there any relationship between the two variables? Is there any correlation between the two variables? And is that correlation significant? These are usually the 4 questions you want to ask when you're trying to define or see if there's some sort of, if you're analyzing two variables together. And again, when I say variables, I mean two columns of data against one another, right? Now, what if we wanted to test the relationship between employees and population density, right? Logically, kind of makes sense, right? If you are in a place that has higher amount of a population, you perhaps want more employees and vice versa, right? Now, these two columns, the employees, if you recall, the employees column is a numeric one. It's numbers, whereas the population density is a categorical column, right? Now, essentially, to test for this relationship, ideally, right, one way to test for this relationship is we would want to, one way to possibly do this is that we would want to convert the employees column, that's numeric, into a categorical data. I'm sorry, I have a typo here, by the way. It says we want to convert population density has to be converted to categorical data. It already is, right? We're talking about employees. The employees column, we need to create some sort of categorical data there. Enter a very nifty little function in R called cut. All right, called cut. And essentially what cut does is that it takes any kind of column of values, numerical column usually, and it'll create groups out of those values. It'll create groups out of those values. So assume for a second that we're going to want to create 2 groups out of the numbers, numerical numbers and employees, right? 2 groups. I can define that if I wanted to, right? I can define that. I can explicitly define that if I wanted to. But in this case, I'm saying, you know what? I'm going to let R figure it out. I'm just going to say, look, create 2 groups divided relatively evenly. Divided relatively evenly. And R is going to go about doing that. So basically what the cut function does is it creates as many groups as you want from the data. Let me show you an example of using the cut function, right, outside of the table right here. So if we go to R right here, again, here's an example. Cut function example. Again, a nifty little tool in R. All right, so let's say I have a vector of numbers. Let's say I got the numbers, let's do 1, 1, 1. Let's do like this, 1, let's keep it simple. Let's do 1 colon 10, right? 1 colon 10. If I call the cut function on it, I'm creating a new vector using the cut function on x, 2, right? If you notice, what just happened to y, right? Y became literally I got these values back. See these values, right? It's probably easier to see these values side by side in a data table. So let me put them in a temporary data table. Again, the watch data table, the original X values, and the new grouping that was put into. All right, here you go. All right. So what happened was the cut function created two different categories, two different groups, and it named those two different groups this and that. Yeah, I know, disgusting names, but you can actually, if you want, you can also define within the cut function, you can define the names you'd like, right? You can do that as well. Let's go ahead and do that as well, just so you guys can see that. So let's add labels, right? Just to make these groups a little bit, the labels of Y, to be a little bit clearer. So again, these are names that automatically the cut function defined for each group between 0.911 and 5.5. You see that? We wanted to divide it between two groups from 1 to 10, and this is the groups they pretty much came up with. So if I rerun this with another parameter called labels, all right, and here now I can give the labels I want. The first label I'll name, I guess I'll name small. Drawing a blank here. Oh, well, you know what? Lakers. Second group will be Nuggets. No, that times me. You know what? Let's just do Batman and Superman. There we go. All right, done. Now you see, we got it actually created the labels. So I put the values in, check out the table, and here you go. 1 was all the Batmans, 1 to 5 are in the Batmans, 6 to 10 are in the Supermans. Alrighty. Okay, now let's say we have a situation where hypothetically, let's see, and let me manipulate these numbers a little bit more, where I can do, let me repeat these numbers instead. That's what I want to do from the beginning. So let me have a 1, 1, 1, 2, 2, 2, 4, 4, 4, 5, 5, 5, right? And then we just throw in an 8, 8, 8 over here. So let's say I have these random numbers right here. And this time, let's create, instead of 2 groups, let us create 4. I'm going to get rid of the labels just so it does it automatically for me. Oops. Didn't mean to do that. There we go. There you go. Alrighty. And again, you create these different numbers right here, these different groups for you to place the numbers in them. So all the ones are in this, the ones and twos replaced in this group, the fours replaced in this group, the fives replaced in this group, and the eights replaced in this group. All right. So even though I want to cut in fours, right? It did cut in fours, but notice that one group tends to be more than the other ones. So it tries to evenly break up the groups, if you will. So I mean, that's basically what I'm getting at over here. When you make the cut is done by evenly. And we can get even more advanced with the cut. You can predefine your own groups, the sizes, where you want the groups to be, right? So the cut is pretty advanced, a little function over here. Now, the question some of you guys might be having is, hey, when they define these groups, how does it work? Like which one goes into which one? So basically, again, on your lower side is the inclusive, on the outer side is the exclusive, right? So that's basically it. If we can do, let's see if I can do an example here. 2 and 4s. Can I? And I think on the next slide we can do an example right there. So here, I don't think we have a 7.5, right? We technically don't have a 7.5. But if we did, the 7.5 would fall into this group instead of this one. So back to our slide at this point. What's happening here is I'm taking the employees column, which is numeric, and I'm going to make a new column called employee factor. All right, close this out. Just comment this out. All right, and now I'm just going to do the cut function, all the rows. I'll call it imp group. What did I call it? I called it imp factor. All right, that's fine. And I did cut. Right, it cut on employees, and just 2. Real easy. And now, right, if you guys were to check out the mark, let's check out the mark table right here. You see you guys have employee factor column right there. Employees, the 5s are falling in there. 7s, 11s are in the second group. 7s are in the first group, and etc., etc., etc. See that? 12. 9 eighths. 12 goes into this group. 10 goes into this group. On and on and on. Alrighty? Okay, so from here, guys, make it slightly bigger. So I have these 2 groups now, and again, I could have defined the groups any way I wanted. All right, I could have defined them any way I wanted. So basically, what happens here is now I can compare these 2 categorical columns. Basically, I want to compare these 2 categorical columns. I want to see how many of the employees are in employee sizes are in the low, medium, highs, right? The low, medium, highs. And this is where I'm going to show you the table function again. And the cool thing about the table function is I can give it 2 of the columns, and it'll basically create something like a confusion table for me, right? So if I literally use the table function here, and I say, you know what, give me mark factor and mark pop density, bam, right? I have my 2 groups, and it's breaking down the low, medium, high. So from here, basically the 3 to, looks like the 3 to 7 point, there's no really 7.5. So from the 3 to 7, I would say the 3 to 7 are going to be, 33 of the 3 to 7s are in the lows, 33 of them, 21 of them are medium, and 22 are highs. All right, fine. This group are our lower end employees. So we pretty much created 2 groups. We'll call it low employees and a small amount of employees and a lot of employees. Over here, it's from basically, I would say 8 to 12, right? 8 to 12. And so our larger companies. So 33 of them are in low populations, 31 of them are medium, and 30 are in high, okay? So here, when we break it down like this, it shows that, our companies that tend to have more employees, they tend to be more in the medium and the higher population densities, which is something we kind of wanted, right? And in this case, our employee companies that have less amount of people, they tend to be more in the lower densities than in the other 2 densities. But it really doesn't seem that much of a difference, right? It doesn't seem that much of a difference. The way to actually view this is to do it visually. Right? Now, how do you compare visually compare 2 categorical columns with one another, right? You use a bar graph, yes, but what you can do is you can subdivide that bar graph between the 2 groups. Let me show you what I'm talking about. Let's run back and do our bar graph on our population density again. I have that here. All All right, I have that right here. Okay, let me get rid of the color part and just have a blue bar graph. Done. See that? All right, now the question you guys have is, okay, what about this second categorical column, the imp factor column? How do we now visualize that? We visualize that by changing, adding another aesthetic within the aesthetics function that is now defined by the fill. Let me explain. All right. So here I'm going to take the fill from here, put it into the aesthetics portion right here. All right. Obviously, I'm going to delete the blue. Now, like I said before, within the aesthetics function, you are designating which column you want displayed on the X or the Y axis, or which column you want used for aesthetics purposes. In this case, we have another column called employee factor. I don't want it on the X or the Y axis, but I do want it used for, but I do want the column used to define the graph in some sort of way. In this case, I want the colors of the bar graph to be dictated by the employee factor. So in here, when I choose now employee factor column, right? The employee factor column, what's going to happen now is that it's going to basically break up the colors, okay, in the bar graph based on the categories. So if I run this, you get something like this. See this? Let me minimize this because it's way too big. All right, you see that? Way too big. All right, so before we had the population density didn't change. It's on the x-axis, low, medium, high. All right, low, medium, high. But what happened now is in my fill, I brought the fill into the aesthetics function and I said, hey, the fill is now not going to be one predefined color. The fill will now be defined by the M factor column, And that's why here you got a little grid over here that's saying, hey, this red is going to be for the values between 3 to 7.5, and this color is going to be the value between 8 to 12, if you will. 8 to 12. All right? For 3 to 7.5 and 8 to 12. So here we can see now visually that populations, cities with lower populations, they're roughly equal. They have roughly equal in size of companies in small companies and the larger companies. In the medium densities, we tend to see, again, slightly more larger companies and smaller companies. In the high one, we tend to see we tend to see a roughly equal break in the high, not roughly equal break, I'm sorry, roughly equivalent to medium in terms of the amount of large amount of companies, a large employed amount of companies, and small number employed companies, right? In fact, if you look at the graph, slightly you can see that in the medium density, we tend to have more of the bigger companies than we do in the high density side. So this is kind of implying to us that, maybe our original hypothesis that, look, if a company's operating in a high or medium population density, its size, depending on the density, its size matters, right? That if it's a higher density population, that company will tend to be bigger. This really is kind of saying that maybe that might not be true. But again, I mean, we're not really sure, but this is what it's implying, the data is implying to us. But again, we're getting some sort of feedback and information from the data. All right. Also, that's basically how we can identify that's basically how we can analyze one categorical data to another. When you're trying to visually analyze two categorical columns, use the bar graph. Again, use the bar graph, but you subdivide it into colors based on the fill. This is what I mean by ggplot talks the language of visual analytics or visual or actually the exploratory data analysis, right? Because with the simple flip of a switch, the simple change in code we did right here, the simple change in code, we literally made Phil go from here to here and gave it a column value, right? We were now able to analyze two columns at once, two categorical columns at once. This is the ease of ggplot in terms of analysis, And the next slide, and in the same slide, by the way, I also analyze what I do now is I'm analyzing population density against marketing total. If you recall, marketing total is it's a numerical column. How do we analyze categorical column with the numerical column, right? How do we do that? Well, that I will do in the second video at this point, because at this point, actually, let's go ahead. Let me finish it up in this video, and then I'll move the next slides over to the next video. So at this point now, I have actually, I might as well just make this video long at this point. So we're almost done. So at this point, let's say I have, again, like I said before, I have the marketing total, which is a numerical column, and I want to compare it to a categorical column, which is population density. We can use our boxes again. We can use our box plots. But what we're going to do now is, and I alluded to this a little before, right? We're going to now use not only the y part, okay, like we did before. Scoot this over a little bit. All right. We're not going to use just the x part. That's what I did last time. I did the y first and I did the x. So I'm not just going to use the x part right here. So on the x-axis, I'll put my categorical columns, right? You always want to put your categorical columns. When you're comparing categorical to numerical, always put your categorical columns on the x-axis. And that's usually the general way they visualize it, if you will. So I'll put my pop density here. All right, done. And now what I will do is, in my y-axis, I'm going to put, you guessed it, I'm going to put my numerical column. I did fill blue. Let me do this a little. It's easier to read. All right, and here you go, guys. Here you go. Now I'm analyzing categorical against numerical data, right? And now, see, the brilliance of this is we can see the distribution a lot clearer. All right. So in your population densities, a total amount spent on marketing on the companies that are operating in towns or cities with a lower population density, we can see the total distribution of marketing we spent over here. Now, hypothetically, I would assume that you spend less on marketing at smaller density. It doesn't seem like it's the case, right? It doesn't seem like it's the case. In fact, the medium company, it's slightly more, but it's around the same kind of spread. In fact, the high one, again, right? The high one tends to be the amount of the distribution obviously is bigger in the high population density cities and towns, but it's relatively almost the same as low and medium. If anything, for some reason, the medium density companies, they tend to skew towards more marketing total, which again would seem counterintuitive to us, right? If you're operating in a let's say you're operating in New York City, you would expect you're spending more on marketing than if you were operating in, let's say, hypothetically, in a city like New Brunswick, which doesn't have the same kind of population. But what our data is saying is that that's not really the case. That's not really the case. So again, there's something here that we're making an assumption on, and our assumption is found to be wrong, right? Which begs the question, why is that? The why questions come up. That is what exploratory data analysis is all about. Oh, by the way, I didn't mention this before, but let me point this out right now. Okay? Notice how the boxes are ordered. Low, medium, high. Why is that? That is not alphabetical. This is not alphabetical ordering. What ordering is this, people? This ordering is our ordinal categorical ordering. Because of the fact that R knows this is a categorical column, it's an ordinal column, and it knows the order, or the order of magnitude, R automatically puts the order of the graphs in the order of magnitude, right? Again, a little detail when it comes to categorical data within R. One of the reasons, again, we do the analysis like that. All right, and now finally, we get to comparing. So we already talked about comparing categorical to categorical data. We talked about comparing categorical to numerical data. And what about the most popular combination when you're doing analysis? Numerical to numerical data. And you guys all know what kind of graph you're going to make there. The all important scatter plot. The all important scatter plot, all right? Right? And how do we do this? Now, there's no scatter function. Let's say we want to compare revenues to Google AdWords. The column revenues to Google AdWords, right? There is no scatter plot feature for that. There's no scatter plot function. What there is something called points. Points, meaning dots, pretty much. Let me just, video is already kind of long, so for sake of time, let's do mark. And I will do, what is it, revenues to Google AdWords, right? And there is no, like I said, there is no scatter plot. It's actually called point. You run this, you get this hideous little graph over here, guys. See that? Right, and this is why I said if you want to change the color for points or borders, right, you need to do color, not fill, but color equals purple. That's all. It changes to purple. All right, and depend how you make this a little bit bigger. All right, now, what do we know about scatter plots, guys? Scatter plots are the original graph used to test what? Correlation. Correlation, right? Which again is leading us to down the rabbit hole to linear regression. Linear regression. So in this case, I have this scatter plot. Now, what kind of correlation are we seeing, guys? If the scatter plot, first of all, looks like a line, then we're seeing correlation. The more of the line it looks like, the stronger the correlation. So here, we are seeing sort of a line or a trend that goes upward, from down here to up here. So what kind of correlation is it? That's a positive correlation. When the pattern is going from down here to up there, that's a positive correlation, meaning that, look, as one column of values increases, the other column of values increases as well. So as revenues increase, or Google AdWords is increasing, revenues increases. And if it went down this way, that would show a negative correlation, that as one particular column increases, the other one decreases. Okay, again, correlation. Now, is it strong? It's sort of strong in the beginning, and then it kind of gets weak. Again, strength is based on how much of a line it looks like. The more it looks like a cloud, the weaker it is. The more it looks like a line, the stronger it is, right? The stronger it is. So now we are getting to some actual statistical functions here. Here, the core function, this basically will tell us how strong of a correlation was there, strength-wise, right? So if you just simply use core, more on Google AdWords to revenues, you'll get a basic value like this. And again, you can use either way to do it. You can do it this way or this way. It does not matter. As you can see, both ways work, right? The core function gives you the correlation between two columns, numerical columns. And look, we got a value of 0.766, right? So firstly, the sign is positive. Let's understand that. Okay, so we have positive correlation. Done. How strong of a positive correlation is it? All right, how strong of a positive correlation will it be? So that value, the closer it is to 1, the stronger that correlation is. Now, These values right here, for some reason, I think this is a typo. I'm sorry. It says the values between 0 and 1. This is a typo. I have to fix this. Correlation, right, is a value between -1 and 1. -1 and 1. Because if the number was negative, that implies negative correlation. If it's -1, that means it's the strongest negative correlation. If the number is 1, the strongest positive correlation. If the number is close to 0, boom, there's no correlation. 0 means there's no correlation. Anyway, there's no relationship between the variables. Now remember, there's a difference between correlation and causation. We're not talking about causation. We're not saying one value is the cause of the other. No, no. We are saying simply there's a relationship between the two. But is this correlation significant? Now, I use that word significant because that is your old stats word, right? That is what stats is all about. Significance, significance, significance. So in the statistical sense, significant means that your correlation is due to circumstances other than random chance, other than random data, other than random errors, right? When we test this, if we want to know if something is statistically significant, let me give you an example about statistical significance. 2016, Joe Biden, Hillary Clinton. They had polling results. Hillary was always on top in these swing states, right? Forget the national election, but in these swing states. Oh, they're always like, oh, she's always top. She's winning, she's winning, she's winning. And then boom, she lost. They're like, how could the polls be so wrong? The polls weren't that wrong. If you guys looked at the values, if these journalists had any kind of statistical training, and they looked at the random error around those pollings, they would have saw that Hillary's lead was not statistically significant compared to Trump's, meaning the error around the data was too large to make a call one way or the other. Or let's put it this way: the lead that Hillary had wasn't statistically significant because there was too much randomness in the data, which meant that she was actually statistically equivalent to Trump, right? Because there's always uncertainty around the data, there's always random noise around the data. For her to be actually statistically leading Trump, right, significant from a statistically significant point of view, then given the random error, she needs to have a greater lead numbers-wise. It had to be much greater than what it was. That's what we mean by statistically significant. All right, that we can be somewhat certain about strongly certain that the values are due to circumstances other than randomness. And of course, R has a nice little correlation test built into it, right, called core.test. Copy this and just do core.test. Bam. And there we have it. All right. And here, you, of course, everybody already taken statistics and linear regression, completely understand everything being said here, right? Right. I mean, you should. I mean, I've had to teach. I mean, I found out on the next lecture, in lecture 4, when we talked about linear regression, that clearly you guys don't remember linear regression or didn't understand it the first time around. So we'll talk about what's going on here in the next lecture. All right. So a little conversation, a little precursor to the conversation around this. The essential idea here is that we want to test what we call the null and alternative hypothesis, which basically means beta equals 0, beta does not equal 0. What does that mean? The null hypothesis is basically saying that this is what we want to basically try to disprove. The null hypothesis is basically saying that there's nothing going on, all right, when we do this correlation. Like when we get this value right here that we have, there's 0.766. The null hypothesis we're testing is saying, hey, you know what? This number is actually statistically 0, all right? The alternative test is saying, no, that number is not statistically 0, therefore implying that it's statistically significant, therefore implying that there is truly a relationship there between the numbers. It's not just a random error. It's not just a randomness in the data. And again, by randomness in the data, what I mean is that if you have a lot of variations in your columns, that will produce random errors when you guys do correlation analysis or linear regression analysis or any kind of relationship analysis between the data, right? So the only way we can be certain, not certain, but the only way we can have some sort of confidence, what is the word I'm using, confidence, in our result is if it passes the null hypothesis test, right? Now, the way we run a null hypothesis test, we use something called either the t-test or the f-test, and it's basically what the t-test is basically the t-statistic. It's basically a t-statistics you're generating, and what that t-statistic is pretty much generating. It's basically asking the question that hey, how much error was in the data between these two columns? All right, how much error was in the data between these two columns, and given the error in the data in these two columns, that value that we were given back, that 0.766, how much of it is explained from the errors in our data, right? So a little more formally, the t-test is basically asking how shocking is the value, right? How shocking is that value, 0.766, given the variation in the data used to derive it, right? So the t-test, if the t-test is not too large, then that's implying, oh, you know what? That value is not that shocking then. That value makes sense given the variation. But if the t-test is really large, right? If the t-test is really large, or the t-statistic is really large, then that's implying, oh, you know what? That number cannot be explained by the variation in the data alone. There's something else going on here. And when we say there's something else going on here, ding, 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 then we're saying, then we're in the realm of something statistically significant. Now, the question you guys ask is, hey, what do we know what's a small t-score? What do we know is a large t-score? Again, we'll talk about the next chapter. We'll get into that next chapter. All right? But there is something called a p-value over here, right? The p-value over here. And usually, this goes to something we call a confidence test. And again, we'll talk about that next slide. But usually, if that p-value, look at this, 2.2 to the power of negative 16. This derives a number like this. See that? That is really, really small. This p-value basically is asking the probability of this t-value, right? The probability of this t-value in a normal distribution curve, normal distribution curve. So a p-value of 0.0000 is basically all the way at the right tip of a normal distribution. What is that implying? That is basically implying that, hey, that t-value, right, given the variation in the data to calculate a correlation, the fact that we got a t-score like that, the variation would generate a t-score like that 0.00000022 times percent chance of that happening. Guys, that's virtually 0%. That's virtually 0%. So the p-value is basically saying, hey, you know what? To get a t-value like that, given the variation in the data, it's like virtually a 0 probability that you would get that value based off just the variation. So if it's virtually a 0 probability chance of getting that value based on the variation in the data of the two columns, then what the hell caused this t-value? What caused that t-value was an actual correlation relationship between the two columns. That's how we basically say, hey, you know what? This value is indeed statistically significant because the t-value was significantly large or greater than the errors in the data that were used to generate this and that. right? So that is why we're pretty much saying that the true, and this is why, if we go back to the null test I talked about, right? This pretty much says, oh, you know what? Saying that the correlation is in actuality the hypothesis that it's actually zero, we actually have enough information, i.e. the p-value in the t-test, to reject this value. Look, the correlation may not be 0.776. Remember, this is just a statistic, okay? It may not be that, but it sure hell isn't zero, implying that there is some sort of correlation and that we should look into this number. We should put more stock into this number that was generated, the 0.766, okay? So that's basically how all this mumbo jumbo, statistical mumbo jumbo works. And again, we'll talk about this more in linear regression. All right, so go ahead, we can run these correlation. We can go ahead and run these correlations between our other two values. Let's run it between Twitter and revenues and Facebook and revenues. All right. So I will do between, oops, Twitter and revenues. And I can get the results. So actually, see my results there. All right. Let's do the core test instead, guys. All right. And I can see, okay, the correlation is much lower. It's closer to zero, right? P-value, and notice the p-value, by the way, here is what? It's zero, but notice now, it's not like as much zero as the first one, all right? So again, I mean, we could take confidence in the fact that, hey, you know what? There is some sort of relationship, and the correlation is truly 0.269. But even then, even if we take this value, we say, okay, this value actually means something, it's a small value, meaning that the correlation between Twitter and revenues isn't that high. Basically, this implies, hey, the money we spent on Twitter really didn't have a relationship to revenues, which begs the question, why the hell are we spending money on Twitter advertising if this doesn't really have a relationship with our revenues? Remember, we're not saying one causes the other. We're just saying there's a relationship between the two. All right? Bam. All right, so now let's do Facebook and revenues. All right. Here, our p-value again to the power of it's to the power of -16. So again, it's virtually zero. And by the way, it's literally telling us the results of the hypothesis. It's saying, look, it's the alternative hypothesis. True correlation is not equal to zero, meaning we reject the null hypothesis, right? And again, correlation is 0.577. So there is some sort of positive relationship. Not as strong as Google AdWords to revenue. Definitely better than Twitter. Definitely better than Twitter. And of course, here, what I show you guys is that, look, I can run both of these guys. I can run both of these at the same time. Ah. All right. If I just pass both of these guys in the dot parentheses, I get a result like this. All right. The only downside is, like, again, it gives you v1 and v2, basically for the first function you ran and the second function you ran. But what it does not do is it doesn't list out, what each one means down the side. Like we got above here. See how it nicely lists out what everything is? Here it just gives it to us in like values. And we pretty much have to figure it out. But we pretty much have an understanding what's going on here, right? Here's our correlation from before. Here's our p-tests. Where's my p-test? Right here. 2.20 and 0.003. Okay, excellent, right here. All right, here we are again. That's what I pretty much thought. Okay, so you can, this I'm just taking an opportunity here to show you, not only just comparing the values, but I'm just showing you an example in R how you can, using the data tables, run as many functions as you want. as many functions as you want. Alrighty, and now let's run the scatter plots on both with revenues, Google AdWords, revenues in Twitter, and revenues in Facebook. All right, for the sake of time, I'm just going to copy these bad boys. Actually, that probably might take more time. But let's go. I do have my scatter plot from before, so I'll just take it. All right, so this one gave me Google AdWords. This one will do it for Twitter. This one will do for Facebook. Twitter. Look at this. Now, already we saw Twitter had a score of like 0.269 or something like that, right? Look at how it looks. It looks like a cloud. There's no correlation going on here, guys. All right, there's no correlation pretty much going on here, right? Visually, at least. All right, let's check out Facebook. So Facebook isn't like Google AdWords, but like I said before, it's better than Twitter. And again, we know that because we ran the correlation before, right? 0.5777. Okay, so that's basically how you can run the scatter plots and check it out visually. Right now, those are our 3 columns, but let's say we had multiple columns with numerical data. Let's say we had multiple columns with numerical data. Let's say we had 100 columns. There's another function outside of ggplot that I want to show you called pairs. And what pairs will do is pairs will run and it's kind of messy here to see. If you guys run it on your machine, you can see it clearer. Pairs will literally create a scatter plot with every column against every column. Let me show you what I'm talking about. Let's do pairs mark. Oh. Let me zoom in. All right, so I have to zoom in for this. And now it takes all your columns and it does literally a scatter plot against all data. Even our employee, I should have gotten rid of employee factor, but even our categorical data, right? Notice our categorical data. So right off the bat, we can see where we have strong correlations, positive correlations. Google AdWords to marketing total. That is strong. That is strongly correlated. What is this implying? This is pretty much implying that Google AdWords probably was our biggest component of marketing total. Look how quickly we can see that, right? Google AdWords to marketing total. Facebook to marketing total, no. Twitter to marketing total, not really. We spend most of our money on Google AdWords, right? And this might account for why Google AdWords has a stronger relationship to revenues, right? So this is a possible explanation. But even though we didn't spend as much money on Google AdWords to the revenues, Twitter is just, I mean, Facebook is in the fight. Twitter is just horrible, horrendous. So again, what does it mean to you? Well, in a meeting, business meeting, translate this into business. In a meeting, you'd be like, you know what? We have to ask the question, should we keep spending money on Twitter marketing data? Or maybe we should go some periods taking the money in Twitter and spreading it around to Google and Facebook and seeing how well we do then, right? But anyway, this is how data translates into a conversation in business, a conversation between you and your bosses, if you will, right? We're not even doing data science here. This is just pure correlation at this point, guys. I mean, we are technically doing data science, but this is basic stuff. All right, and now we can also get our actual correlation number between all our numerical columns. Now here we have to actually take a subset, guys, because correlation only works on numerical data, right, on numerical data. So that's why here what I do is I will only specify, again, I'll specify all the rows, but I will only specify certain columns. Now notice here in the column section, this is new, you've never seen this before. I'm putting numbers in there. What do the numbers mean, guys? The numbers, if I have numbers in the column section, that is basically saying, hey, choose a column based on the order of the column. So here, if I go to my mark table, the first column is Google AdWords. This is 1, 2, 3, 4, 5, 6, 7, 8. 7 and 8 are categorical columns. I will leave them out, so I'm only going to include the first 6 columns. So this is an easy way to also select columns using numbers instead of the actual names. Right? And if I do core, and I say, hey, you know what? All the rows, just give me the 1 to 6. 1:6 again means 1, 2, 3, 4, 5, 6. Bam! It's going to run a correlation. It's kind of easier to see here. It's going to run the correlation numbers between all the numerical columns, right? Numerical columns. Again, marketing total, Google AdWords. It's high. We saw that from before. Revenues and marketing total. Revenues, marketing total. It's pretty high, right? Again, relationship between how much money we spend and our revenues. That's probably a positive sign. And what else is high? We see revenues and market total we got. Anything high? Market total Google AdWords, that's pretty high. That is the highest, actually. And the other, I would say the second highest thing we see is marketing total and revenues. That's a good sign. And the third highest then, well, check this out. The third highest, actually, I'm sorry. The third highest is actually revenues and employees. Look at that. There's a relationship, a positive relationship between revenues and the number of employees. Interesting. All right, interesting. So anyway, this is how we can basically use our basic statistical analytical functions to basically do some sort of exploratory analysis on the data and generate observations, and more importantly, generate questions on the columns, unique columns one by one, and more importantly, relationship between the columns. Relationship between the columns. All right. So at this point, I will end the video, and the next video for the slides will be basically. So I mean, look, I showed you ggplot. We did a little exploratory data analysis, right? But again, I was going into the basics. Now, what I want to do is I'm going to show you. Going forward, we're going to actually, from slides 25 to 36, you're actually going to do some actual visual analytics. And you're going to do it on a data set, a very famous data set, the Titanic data set. This is the real Titanic data set. All right, this is the real Titanic data set. And I got to actually change these. I thought I already changed this slide, but let me change the slide and repost it. But anyway, hopefully in the video, you'll see. Oh, I probably have in the video. Hopefully, I fixed it. I corrected it in the video to use the right functions. But anyway, so this is the real Titanic data set. This is a very famous data set used in data science in the terms of doing visual analytics analysis. Right? I have students that have actually taken what I showed them and actually have done blogs on it. Right? Maybe some of them did videos. I don't know, but but again, this is something every university, all the top universities, they use this data set to basically show you how to visual analytics in play, right? And this is the next video. So I closed out this video. I apologize for the length, but I figured I might as well just have finished off the first part of exploratory data analysis. And then the next part, guys, you're going to actually do some actual visual analytics. All right, have a good day. See you in the next video.